Okay, so we'll just go to 7b. We're integrating to the inverse trig functions. Now what I'll talk about here is what the inverse trig functions are. So we're going to have a little bit of a recap of functions and relations. That's going to be good. And then we'll just get into the examples, and then a bit later in the lesson, maybe after recess, we might look at a proof. We may even venture into 7c today. This exercise isn't too long, it's quite short. We'll see how we go with time. So firstly, let's just remember, like if we have the function y equals sine x, okay, this is what its curve looks like, right? And we can even go this way a little bit. And then what I want to remind you of is the inverse function, okay? So if we have f of x is sine x, then f of minus 1 of x is going to be the inverse function. Now we call that, so it's sine of minus 1 of x, we call that, the proper way to write is arc sine of x. Okay, that's what it actually means. That's where the arc comes, arc sine of x. And what it is not, okay, sine to the minus 1 of x, it is not sine of x to the power of minus 1. Because this is 1 on top of sine of x, which is cosec of x. Okay, so you covered them in semester 2 of spec last year. And this is where they start to pop up a little bit more now, is the inverse trig ratios, okay? So here we go. So we've got arc sine of x, it is not the same as 1 on sine of x, all right? It's the inverse function of sine of x. Now, I might edit my graph a little bit here as well, just to demonstrate what is an inverse function. And what I'm going to do is I'm going to sketch the line y equals x. Interesting colour. Okay, y equals x. And so now if I have the sine function, all right, sine has a maximum at x is pi on 2 and y is 1. Now pi on 2, that's about 1.57. So its maximum is going to be about there, and then it starts going back down. And similarly, it has a minimum at minus pi on 2, not minus 1. It's minimum 2. Okay. So this is what the function is going to look like, right? Now, we can sketch an inverse function provided it passes two tests, the horizontal line test and the vertical line test. And so all that's a matter of doing is going, okay, yep, it passes the vertical line test. The line does not cross the function more than once, but it doesn't pass the horizontal line test. We can see it fails here. And so the technical definition is, for it to have an inverse, it must be 1 to 1, where each x value has one unique y value, okay? And each y value, one unique x value. Now, one thing we can do to make out an inverse is we can restrict the function. So if I graph the function from minus pi on 2 to pi on 2, okay, now all of a sudden it passes both tests. It passes the vertical line test and the horizontal line test. So now this function has an inverse, and we can sketch the inverse. All right, so if I'm going to sketch the inverse of this function, all we're doing is a reflection about the line y equals x. So I'm going to sketch this up here like this, all right, and I'm going to sketch this down here like this. Now these coordinates, remember, for an inverse function, the x and y coordinates just swap. So if I've said this is x is pi on 2 and the y value is 1, then that means the coordinates here are going to be 1 and pi on 2. All right, over on this function here, at this far extremity here, we have x is minus pi on 2, y is minus 1, and so they will swap. Okay, so this function that I've sketched in my purple marker here, that is arc sine of x. All right, so that's what the inverse trig function is. Now we have the rest of those listed there, so we've got cos x and tan x and the inverse functions there. And just remember, it is not the same as cosec of x, okay? It is not the same. That's the reciprocal, so just language. This is the inverse function, this is the reciprocal function, okay? 1 divided by reciprocal function. All right, so what we'll do, we'll rip into our examples, and then I'll go through a proof of one of them. I'll make a cool proof that we can look at. So we're just introduced to some more rules. So we've got up the top there a number of boxes, and all we're trying to do with our examples, so example A we have is the integral of minus 3 on top of the square root of 16 take x squared, is we're going to try and make it resemble one of the forms that we have up here in the boxes. So if we're looking at it, all right, if we can pull the 3 out the front to begin with, so we have 3 times integral of negative 1 on, and I'm going to change this 16 to 4 squared, take x squared, and now we can see really clearly in the bottom box, it's the one on the left, all right? That our A value corresponds with 4 and everything else matches, okay? So once we have it stated like that, we can go straight to the integral, okay? Firstly, this 3 is just going to hang out the front, and this part is going to integrate to arc cos of x on top of A. The A value in this circumstance corresponds with 4, and then plus c. Okay, so identify which one does it look like, identify the A value, integrate. Okay, let's go to B. We have integral of 15 on top of 1 on 25, take x squared. Okay, pretty similar. Don't forget my dx's. Let's pull 15 out the front. Try and identify this as some A value squared. Now the difference with this one is that we don't have that negative sitting out the front. So it's the top box on the right. We have A squared take x squared, 1 on top of A squared take x squared. So the 15 just hangs out, and we're going to have arc sine of x on top of A. Our A value is 1 on top of 5 plus c. And x divided by 1 on 5, that's going to be 5x. I'll show you why that's true. If we have x divided by 1 on 5, what we're going to do is we're going to separate this to, we have something divided by a fraction. We need to first express this as a fraction. So x by itself, well, that's the same as x on top of 1. So now we have one fraction divided by another, and whenever we have A on B on C on D, it's just A times D on B times C. So we'll have x times 5 on 1 times 1, 5x on top of 1 is 5x. So that's how you can simplify those quickly.
Can you think of it like 5 to the power of -1, so then you just put it up the top because it's like a negative power on the bottom of the fraction?
Yeah, that's a great idea as well. Yeah, so 5 to the -1, so then we have x on top of 5 to the -1, take it to the top. Yep, I like thinking about it like that too. Yep. Yep. Yeah. Cool. All right, so we've got 15 arc sine 15x. Let's have a look at C. So we've got the integral of -5 on top of x squared plus 25. Okay, so we're looking for which form does it take. Now, this negative, we can pull that out the front if we want to, and I can see it's pretty well matching the dot point, the third box to the one on the right. So if I pull that negative out the front, we can see we have 5 on top of 5 squared plus x squared. Okay, we can rearrange the order of that. 25 plus x squared is the same as x squared plus 25, so that doesn't matter. And now we can see it lines up exactly with that form. So this will integrate to negative arctan of x on 5 plus c. Okay, we've got one more overleaf, which is a definite integral. So we're going from 0 to 1 of 1 on top of the square root of 1 take x squared. Okay, so looking over, trying to identify the formula associated with it. It's just the first one listed to us. So the first box, 1 on top of the square root of 1 take x squared. This is going to integrate to arc sine of x plus c. Sorry, no plus c. Why? Because it's a definite integral. We've got a boundary, which means we're now going to perform the fundamental theorem of calculus. So this becomes arc sine of 1, take arc sine of 0. Okay, so how can we evaluate those? Well, what is arc sine? Like, if I write it a different way, it's going to make a lot of sense for you. Arc sine of x is the same as sine minus 1 of 1 and sine minus 1 of 0. What it means is, what is the angle that gives us the sine value of 1? What is the angle that gives us the sine value of 0? So, if you think about your unit circle here, the sine value is 1 at this location, the angle is pi on 2. And here, the value of sine that has an angle of 0, sine is 0 here and the angle is 0. So our answer to this definite integral is pi on 2. Now, can anyone have a wild guess? Why would I not consider this value over here? Because the angle is 0 over here.
Because isn't that like out of the domain?
Perfect. Yep, that is outside the domain. The inverse function only exists between minus pi on 2 and positive pi on 2. Well done. All right, so let's leap into 7b, and we might entertain a bit of a proof after recess.